So yesterday we definitely did way more complex Newton's second law problems than this one. Because this one gives you the net force. We did, on all the ones we did, we had to calculate it first, okay, using the sum of all forces. Okay? On this one, they just outright tell us that the net force is 3.0 newtons forward. Okay? And it's on a mass of 0.15 kilograms, and they're just wanting the acceleration. So that's pretty straightforward. We just have to manipulate to get acceleration. Okay? So that's going to be 3 divided by 0.15, and which should give us 20, right? Yes. Meters per second squared forward. Okay, I will never give you one that easy because I'm not that nice.
You wrote it wrong. It's not 0.01.
Oh, sorry, 0.15. Okay, everybody all right with that one? Okay, I want you guys to try these ones. They're, yeah, also easier than anything you're going to get from me. Okay, see how you do with those two. Like I say, they're pretty straightforward. Okay, so on this one here, this one involves you reading a bit more carefully. Obviously, the other ones are pretty simple. The math of this one is not difficult at all, okay? But it's the context of the question that sometimes causes people to make a silly mistake. Okay? So we got 2 athletes on a rowing team or training. Athlete A is a mass of 65 kilograms, athlete B a mass of 70 kilograms, and the canoe a mass of 20 kilograms. Athlete A can exert a rowing force of 400 newtons forward, B 420 newtons forward. In the water there's a resisting force of 380 newtons. We're looking for the acceleration of the canoe. So this is a bit more like what we did yesterday. Okay? You still have to do a sum of all forces calculation here. All right, give you a minute on that one. Okay, so with this one here, we've got our mass. How much mass is being accelerated? 155 kilograms. Okay, we have the 2 athletes and the canoe. The common mistake that I see here is people just put 20 kilograms in there because they just do the canoe. Well, it'd be pretty interesting to see how they paddled it if they weren't inside. Okay, so it's just one of those things. So we got 155 kilograms here. Okay, we know that we have a force of 400 newtons forward, force of 420 newtons forward, and a force of 380 newtons backwards. All right, so those are our 3 forces. So now we can calculate F net by going vector sum of all forces. So we'll go 400 plus 420, okay, which is 820 minus 380. We're looking at 460? 440. See, I shouldn't do it in my head. I should just punch in the calculator. Okay, newtons, forward. All right, what's my next step? So that's one way to calculate F net. What's the other way to calculate F net? Isn't that the other way to calculate F net? Okay, since I know what F net is, and I know the mass, can I use that to get the acceleration? Okay, that's what my next step is. Okay, acceleration is F net over m. Okay, and that's going to be 440 divided by 155 kilograms. Okay, so 2.8. We only have 2 significant digits here. So 2.8 times, or 2.8 meters per second squared forwards. Okay, so if you recall, when I was talking about Newton's second law, I said in basically every Newton's second law question you are going to do, you are going to use both methods of calculating F net. Okay, F net equals m times a, which equals the vector sum of all forces. Okay, do we have to use both there? And we're going to have to use both on most of the problems that we do, with the exception of the super easy ones that we already did, and we'll probably never see one like again. Okay? They're always going to have to do some sort of vector sum and then go to F net equals m times a. Or they give you mass and acceleration, 2 out of 3 forces, and ask, what's the other force? Okay, so this question could have set up that way and said, the acceleration of the canoe is 2.8 meters per second squared forward when these 2 people and their canoe are being rowed. Okay, the forces of the 2 rowers are 400 and 420. What's the resisting force against the canoe? Okay, and then I would have to go, all right, I know A and M, so I'll calculate F net that way. Then I'll subtract the 2 forces I know, and that'll leave me with the force I don't know. Okay? There's really only those 2 ways that a Newton's second law question is going to go. You either have mass and acceleration and are looking for forces, or you have forces and you're looking for acceleration. It's one or the other, really. Okay. This one is a reading comp question. There is a lot of extraneous information in it that you will not use. This is not a mathematically challenging question. It's a question that can trick you. All right, so give it a try. See if you get it right. Okay, correct answer is 4.7 meters per second squared forward. Okay, so in the 4-man's bobsled event, the maximum mass of the bobsled, 2 riders and a pilot and a brakeman, is 630 kilograms. So, it doesn't matter to me. I can't use that number in this question anywhere, because during the part of this question that's where they're actively pushing, 2 of them aren't in it. Okay, 2 of them are still pushing. Okay, a 4-man bobsled team consists of, a pilot, a brakeman, and 2 guys with really strong legs who push hard. Okay, they just sit in the back and act as ballast after they have pushed the bobsled and basically move their heads when they go into a corner, and that's it. Okay, so they're not in the sled right now. The pilot and the brakeman are. Okay, so my mass that's being accelerated is not all of them together. Okay, it is the 225 kilogram bobsled. Okay, so now we're up to 323. Okay, and now we're up to 420. Is that right? Okay, 420 kilograms is the mass that's being accelerated. Right? Then we can put the forces on our free body diagram. Okay, so we are looking at 1,200 and 1,220 newtons forward. Okay, and we are looking at a force of friction of 430 newtons. Okay, and this number, the 1,300 meter course, also completely irrelevant to what we're doing. So a question sometimes will do that. It will give you information that seems like it might be important just to throw you off. Okay. So here's my free body diagram. What's my next step? Before I do that,
calculate the net force.
right, before I do that, I'm going to calculate my net force. Okay, so I'm going to do vector sum of all forces. So that'll be negative 430 plus 1,200 plus 1,220. Okay. So 2420 minus 430, okay, 1,990. Seems right. Probably did that right. Okay. Okay, so 1,990 newtons forwards is my net force. And now, what do? Now I manipulate m times a equals F net, because I just calculated F net with the vector sum of all forces. So I just divide both sides by m and plug in my numbers. 1,990 newtons forward divided by 420 kilograms, and that should give me my 4.7 meters per second forward. Okay, everybody all right with that? Right, so.
Shouldn't it just be positive 4.7, because they didn't say forward in the question?
I would probably have to accept both given the wording here. Yeah. Because it never outright says positive either. Yeah. So it's contextual. I would say your vector on that would be anything contextually appropriate. Like backwards would not be contextually appropriate. Yeah. You could even say down the track, right? That would be contextually appropriate. All right, so all I'm trying to do with these ones, I'm not trying obviously to challenge you mathematically, okay? What I'm trying to do is just show you the pattern that goes along with Newton's second law problems, okay? The hardest part of that pattern, we haven't really gotten into any tough ones yet, and that is, I got a whole bunch of forces and I gotta figure out how they add up to get the net force, okay? Because after that, it's just m times a, it's like manipulating v equals d over t, that's not overly difficult. All right, now, these are also not mathematically difficult, but they are a very typical type of Newton's second law question. Elevator questions. Okay, I'm sure you've all ridden in an elevator before, yes? Okay, is there a time in an elevator where you feel lighter? When is it?
When it's coming to a stop.
Actually, you're gonna feel a little heavier when it's coming to a stop. When it what?
Depends on which direction.
It does depend on which direction. Right. When you first start to move downwards, when the elevator is actually accelerating downwards, which is only for like a second and a half tops, okay? You feel a little bit lighter when it first starts to accelerate, and then it moves at a constant velocity. You don't want an elevator that accelerates all the way up or all the way down because it gets going really fast, and it would be a very uncomfortable ride because it would be hard to stand up. Okay, so when the elevator first starts moving, especially if it's kind of an older, sketchy elevator, okay, it feels like it's going to drop, right? Because the brake just kind of lets go and the motor doesn't take up right away, and there's that feeling of your stomach going up into your throat. Okay, that's when you feel lighter. And you feel lighter because in that situation, the floor isn't pushing on your feet quite as hard as it would if it wasn't moving. Okay? Because it's trying to accelerate away from you, you feel a little bit lighter. On the other side of that, when the elevator is trying to accelerate you upwards, it pushes against your feet a little extra, okay, to get you moving in that direction. And so as a result, your knees kind of buckle and you feel the floor pushing against you and you feel a little bit heavier. In fact, if you were to stand on a scale in the elevator, people would think you were weird, but, okay, if you did, when the elevator first started to move down, you would read lighter than normal. When it first started to move up, the scale would read heavier than normal, because all the scale reads is how hard is the floor pushing back up on your feet. Okay? Everyone follow me there. So, there's two forces at play here. Your weight and your apparent weight, or the tension in the cable pulling the elevator upwards. Okay? We use the word apparent weight because it's how heavy you feel, not how heavy you are. Okay? There's all kinds of situations that can make you feel heavier or lighter than you actually are. We're going to look at lots of those in this course. Okay? Lots of them have to do with going through loops, okay, on a roller coaster, or if you've ever gone over a hill in a car or on a bike really quickly. Okay? You ever notice that you feel kind of like maybe you've done that on the speed bump out here? Okay? You shouldn't. Okay? I actually saw somebody hit that thing and like launch once. Yeah, it didn't end well for the car. Because when the car hit the ground, well, the stuff that's underneath that's supposed to be this high off the ground wasn't. And it hit the ground and dragged, and then pieces came off. The car ceased to move in a forward direction after that. Okay, so don't try that. It's not only dangerous, but it'll probably wreck your car. Okay, so we've got apparent weight. In that situation, if you were to launch, you would feel apparently weightless because you and the car would be falling at the same rate and thus would not push on each other, and so you wouldn't feel any weight at all. Okay? And it's the same feeling you get if you go over a bump quickly. Okay? You go fast enough that you have enough inertia that you want to keep moving in a straight line. Okay? And so you actually don't feel as heavy as you would in a normal situation. If you go down the bottom of a loop, okay? When you get to the bottom, your inertia wants to keep going down, and so the car has to push harder on you, and you feel a little heavier. Okay? You feel kind of pushed into the floor a little bit. Okay? All right, so if we're looking at an elevator, okay, we are going to have a couple of forces. Okay? They're usually going to identify either the force of tension, which is essentially how hard the cable is pulling upwards. That force is also your apparent weight. Okay? It's how hard the floor pushes up on you inside the elevator. Okay? And then we've got the force of gravity, which is the weight of the elevator or the occupant inside or both. In order to calculate weight, we use this formula. Looks kind of like the one we've been using. Any force, any individual force, can be calculated by taking the mass of the object and multiplying it by the acceleration that force produces on its own. Which is why we can calculate the force of gravity by multiplying the mass times the acceleration that gravity produces by itself, which is 9.81. Okay, so little g always stands for 9.81. Okay, so this question wants us to calculate the acceleration of the person. In order to get that, what do I need? Two things. What two things affect the acceleration of something?
The force and
The
the mass.
force and the mass. Okay, so I need the net force and I need the mass, which they told me. The mass is 600 kilograms. Okay. Is there more than one way to get F net? Okay. Can I get F net using the sum of all forces? I can, because they tell me the elevator cable is exerting a force of 6,500 newtons up. So this force here, okay, this force is the force of gravity. They don't tell me what it is, but they tell me the mass of the elevator, and I know the acceleration due to gravity. So I can calculate the force of gravity by simply going 600 kilograms times 9.81. Okay, I think it's 5886, right? Okay, can I find the net force now? Yes. Okay, so my net force is going to be 614 newtons up. Can I calculate the acceleration of the elevator? Yeah, so it's going to be just over 1, right? So I think we have 3 significant digits there. So we can go 1.02 meters per second squared. What's my vector? Up, yeah. Always the same as F net. Whatever the vector on F net is the vector on acceleration. Okay, everybody kind of follow how the elevator question works? They're very straightforward, okay, which is why you see them a lot, okay, in questions. What we have to understand is they can really mess up the wording in these to try and trick you into something. They can say, you know, the apparent weight of the person inside the elevator is this much and their mass is this much, okay? Or I've even seen sometimes where they say the apparent weight of the person is this much, okay? The acceleration of the elevator is this. Calculate the mass of the person, okay? And you have to kind of work backwards to get it, okay? Yeah, so it's all kinds of different ways to ask an elevator question, but when it comes down to it, an elevator question is 2 forces. The upwards force and gravity. Okay? That's all that acts on an elevator. Okay, I want you guys to try number 1. Okay, so it's the same elevator. So that elevator is 600 kilograms. Okay, and now the cable is exerting this much force instead. Okay, so calculate the acceleration of the person inside the elevator, which is of course the same as the elevator. And then we'll look at number 2. so for question number 1, we have the same elevator that we had before. So we have a 600 kilogram mass being pulled upwards by 5,200 newtons worth of force and being pulled downwards by the force of gravity, which is m times g. And since it's the same elevator and it's still on Earth, we would assume, okay, that this is still 5,886 newtons, okay, which is 600 times 9.81. Are we all right with the setup? Okay, what's my next step? Calculate the net force. So I got to do vector sum of all forces right now. So F net, okay, will be 5,200 plus negative 5,886, okay, which is going to give me 686 newtons, and that'll be negative or downwards, okay, in this case. All right, now that I have that, I've done the vector sum of all forces. How do I get acceleration? Now I use F net equals m times a, right? Okay, like we said, we're always going to use both in every question we do. We've done the hard part, getting the vector sum of all forces. Now we just plug that into F net equals m times a in order to get acceleration. So 686 negative, because it's down, okay, divided by 600 is going to give me my 1.14 meters per second squared down. Okay? Everybody all right with that?
Can you just get like the force divided by the mass, and then from that, just subtract from that point?
Force divided by the mass.
So like instead of like doing mass times like gravity, just like have the original force divided by mass, then subtract it from that point.
Okay, so you're actually on to what I'm going to do in the next question. You're doing what we call the differential acceleration method, okay? Which is what you do if you don't have mass. You can do this one that way, and if you're comfortable doing that, you're going to arrive at the right answer. I never explain it that way at first, because sometimes it's confusing, but yeah, good on you. You figured out that you can do it that way. Okay, so what a great segue into how to do the next question, okay? In the next question, we're told that this electric chain hoist can exert a force of 2,850 newtons up. Okay, so if I start my free body diagram, okay, I don't know what the mass is, but I know there's 2,850 newtons up. Okay, and they want, so this is lifting an engine out of a car. The acceleration of the engine is 1.5 meters per second squared up. What's the mass of the engine? Okay. Does it seem like they give me very much information? All right. Here's what I have to understand. Yesterday, when I was telling you about this formula, I said F net is mass times acceleration net. But I said we never write the net on the acceleration because it's kind of a given. But here's where that's kind of important. Even though we never write it, here's why that's the net acceleration. Any force can be calculated with this formula. We just used it to calculate the force of gravity. Any force is equal to the mass times the acceleration that force would produce by itself. Okay, everybody follow me there? All right? The net force is the mass times the net acceleration. The force of gravity is mass times the acceleration due to gravity. By the same token, this force, the force of the hoist, would be the mass times the acceleration the hoist would produce if there were no other forces present. Because then it would be the net force. Right? So basically we're saying any force can be calculated by going mass times acceleration. Okay? So in this question, the other force involved is gravity. I don't have the mass. to calculate. My problem is I also need the mass in order to calculate this force. I can't get the vector sum of all forces without it. So I won't. Okay? So here's what I'm going to set up. We know that F net is the vector sum of all forces. In this question, that's the force of the hoist plus the force of gravity. Now, I'm going to expand this out. F net is mass times the net acceleration. The force of the hoist is mass times the acceleration of the hoist. And gravity is mass times acceleration due to gravity. So in every question we've done, the acceleration and the net force have always had the same vector. Agreed? And that's true for those other forces that I put in there, right? Force of the hoist is up. The acceleration the hoist would produce would be up. Force of gravity is down. Acceleration due to gravity is down. What's in every one of those terms right now? Mass. It's in every term. I can cancel it. Now, probably some of you are going, here, this is what you're supposed to solve for, you idiot. Like, what are you doing? You can't cancel the thing you're trying to solve for. You're right. I can't solve for it if I cancel it, but I'll come back to it. Okay? I'll come back to it. Right now, I don't have it. So I'm going to get rid of it. Is this okay? Like, this kind of makes sense, right? If the forces add up to net force, the accelerations should add up to net acceleration. This is how we add any vector quantity, right? We put them together. So, do I know this one? Do I know little g? Do I know this one? Yeah, they told it to me in the question. They said the acceleration of the engine is 1.5 meters per second squared up. That's the result of the net force. So I know A net and I know G. So I can calculate the acceleration of the hoist. And I probably don't. So Coder, remember you're supposed to find mass? I do remember that. But if I can find the acceleration of the hoist, I already know the force of the hoist. I can get the mass that it's pulling on from there. Okay? This is what we call the differential acceleration method. We almost never use it, but it's just being explained so that you understand acceleration and force work the same way. Okay? The accelerations can all be added together to get a net acceleration, in the same way that all the forces can be added together to get the net force, because they're all dependent on each other. Okay? They're all the same. They all go in the same directions. All right? Everybody okay with that idea? All right, so with this one then, okay, I'll take my net acceleration, I'll look for the acceleration of the hoist. So that'll be 1.5 minus negative 9.81. That's my net acceleration minus the acceleration due to gravity. Okay, so 1.5 minus negative 9.81, right, gives us 11.31 meters per second squared. All right, so if there was no gravity, that hoist could accelerate the engine at 11.31 meters per second squared. Okay? That makes sense. It should have to pull harder than gravity. If it's going to pull something up, it's got to pull harder than gravity. Okay? So that's the acceleration the hoist could produce by itself. Now I'm going to take that back over to this formula, okay, and use this number, force of the hoist, this number, which I just calculated, to solve for mass. So 2850 divided by 11.31 should give me that the engine is 252 kilograms. That's over 500 pounds. Engines are heavy. I don't know if you've seen all the Fast and Furious movies, but there's one scene where Dom knocks the engine hoist and then reaches over and grabs the chain and holds the engine over somebody okay, with one hand. Of course, they zoom in on Vin Diesel's like massive arms, right? The whole purpose of the shot was to say, hey, I've got big muscles, but okay, yeah, you're not going to do that. Nobody, even The Rock, when he's like fully juiced, okay, is not going to hold that on a chain with one hand at length. Okay. I don't know if you've ever seen like those strongman competitions where they make them hold weights out at arm's length and how long they can do it for. It's really hard. Holding an engine like that, you know, like 500 pounds. Okay, so let's have you guys try this one. It's a differential acceleration question. Okay, so I'll just put that out there to start with. It works just like the engine question we just did. So, a skydiver is an elevator. This is still an elevator question. There's just no elevator. Okay? But there's a force upwards and there's a force downwards. Anything that's affected directly by gravity, okay, and falls or rises vertically upwards is essentially an elevator. Okay? So what we have is the force of friction, okay, or air resistance acting upwards on the skydiver, and the force of gravity acting downwards. Okay, so they've kind of done the free body diagram here, except they have not labeled that this force of friction is 250 newtons. Right? So what we know is that the net force here is going to be the force of friction plus the force of gravity. Okay, we are looking for the mass of the skydiver, and we know that the net acceleration of the skydiver is 5.96 meters per second squared. Okay, so if I expand this out, mass times acceleration net, force of friction times acceleration due to mass times acceleration due to friction, plus mass times acceleration due to gravity. So now I know I can cancel the m's, and I know the acceleration due to friction, and I know the net acceleration. Sorry, I'm looking for the acceleration due to friction. Okay, and I know the force of gravity, or the acceleration due to gravity, and the net acceleration. So I'm going to go net acceleration minus acceleration due to gravity equals the acceleration produced by the force of friction. So that'll be negative 5.96 minus negative 9.81 equals the acceleration due to friction. Okay, why was it important to make the 5.96 negative?
Because it's going down.
Right, and if I didn't, I would get that the force of friction makes the skydiver fly upwards. Okay, which is obviously not what's going to happen here. All right, so the acceleration due to the force of friction is 3.85 meters per second squared up. Now that I have that, and I know what the force of friction is, I can go back to this. The force of friction equals mass times acceleration due to friction. Okay, I can divide both sides by the acceleration due to friction, and that will help me calculate the mass. So I'll take my 250 and divide it by my answer there. All right, so the skydiver is 65 kilograms. Again, I cannot remember ever putting a differential acceleration method question on a unit exam, and I have no plans to do so. Okay? It's just to illustrate to you that force and acceleration have the same relationship. They add together in a vector manner, okay? Because their vectors are all the same. Any force produces an acceleration with the same vector as the force. Okay? That's really all this is designed to show. Okay, try this one. It's not differential acceleration. Okay, it's just an elevator. Okay, a bungee jumper is an elevator. Okay. And see if you can get the acceleration the instant that the cord begins to pull upwards. Because obviously her acceleration when she first jumps is 9.81 meters per second squared. Okay, she doesn't start to slow down until the bungee cord takes up and starts to stretch. Okay, so they're telling you the force of the bungee cord is 825 newtons up. Okay, all right, give that one a try. We'll go through it here in a minute. So on this one here, we have the bungee jumper. Okay, and she's 55 kilograms. All right, we have, what force is this? Force of gravity. Okay, which we can calculate by going 55 times 9.81. Okay, so 539.55 newtons. And we've got the force of the bungee cord. Okay, and that is 825 newtons. Okay, so I've got the two forces. Can I find their vector sum? No problem. All right, so F net is going to be 825 minus 539.55. All right, 285.45 newtons. Up is my net force. All right, so what's her acceleration? Well, acceleration is F net divided by mass. So this is a pretty basic elevator type question. Okay, we take our 285 and we divide it by 55, and we should get 5.2 meters per second squared up. Okay, everybody all right with that? All right, so in question number 2 here, it says the velocity to the 55 kilogram woman at the lowest point is 0 as the cord stretches to its maximum. So if you've ever seen somebody bungee jump, okay, they go off, they fall in free fall, then the bungee cord starts to take up, okay, and it stretches and slows them down, slows them down, slows them down, and they stop for an instant before they're shot back upwards by the elastic force in the bungee cord. Okay, but it's the opposite of what happens when you throw something up in the air. Okay, it slows down, slows down, slows down, comes to a stop, and then falls back to earth again. Okay, well, bungee jumping is the opposite. You're trying to fall to earth, but the bungee cord prevents it, hopefully. Okay, so at that lowest point, you stretch the bungee cord, stretch it. Okay, when you're at the very bottom, your velocity is 0, but your acceleration is its maximum value, because that is where the bungee cord is stretched the most and is exerting the most force. Okay, at this point here, okay, it's saying that it's just starting to take up. So this is not the maximum force the bungee cord can exert. Okay? If you recall, in Science 10, you did that lab where you pulled on the spring, okay, and you measured or on the rubber band, you used the spring scale to pull on the rubber band, okay, and the more you pulled, the harder you had to pull. Okay, like the further you stretched it, the harder you had to pull. Any elastic object, that's the case. So when she's at her lowest point is actually when her acceleration is at its maximum. Because you got your force, the mass isn't changing, okay, but as this force is changing, so is the acceleration. So where would she feel heaviest? At the very bottom. Because that's where the cord would be pulling on her the most. All right. Trying to decide whether I want to go into system questions today or whether I want to just have, we'll do system questions tomorrow. Okay? I want to have you just do some easier Newton's second law ones for today. So we got all these system questions here. That's a static question. That's a system question. See, this is where we're going. See how much stuff there is still? Oh, I don't have any on here. Okay. Let's go to your digital workbook. There's a couple there I want you to do. But it's me. See? My password. It's right there. It's the same as yours. It's all dots. Everyone, as soon as I said, there's my password, everyone's like, what? Okay. What are the chances I picked the right one? Yes, Exactly. Well done.
Just put the second.
There we go. Unit 4.
Okay, so this worksheet is the start of Newton's second law. And the first question is like ridiculously easy, okay, like it's already beneath you. Okay? So give these a try here, okay? Let's say try maybe the first, I don't know, 7. Let's actually have you guys do number 8 first. Do number 8 first, because this is a good one. It's an elevator question. Okay, I'll tell you that right now, but people forget something on this one. So let's try number 8 first, and we'll go over that one as a group here in a bit. Okay, so the thing to remember about number 8 is that it's an elevator question, and I may have spoiled it for you when I told you that. Okay, but I have put a question as simple as this on a unit exam in the past, and had people bomb. Absolutely bomb. Because they forget that when you throw something up in the air, 2 forces are acting on it. Gravity, that's the one they forget, and the applied force that you're using to throw it into the air. Okay? So an 11 kilogram object, okay, is thrown vertically into the air with an applied force of 145 newtons. Okay, what's the initial acceleration of the object? And people go, oh, that's easy. I have the net force right there. And they just go 145 divided by 11, and they get way too big a number because they forget that if that was the way things worked, it wouldn't come back. Okay, you could throw something into orbit if that was the case. It would also be bad if you jumped, because then you could jump into orbit. And, well, there's no air out there, so it would work out badly. Okay, so we've got the force of gravity right here. All right, so 11 times 9.81 gives us that 107.91 acting down. Okay, and now we get a much more reasonable number for the upwards acceleration, at least while it's in the person's hand. Once it leaves the person's hand, its acceleration will be down at 9.81 because that force is gone. Okay, once it leaves my hand, I'm no longer applying that force to it. All that's acting on it then would be gravity, and then gravity would be the net force. Okay, so F net is going to be the vector sum of all forces, 145 minus 107.91. Oops. Okay, so 37.09 newtons. Up. Okay, and I can calculate the acceleration. F net over m. Okay, so 37.09 over 11, and that should give me my 3.37 meters per second squared up. Okay, so it's not a mathematically challenging question, but had I not said to you, in fact, I'm going to try this, I'm going to do an experiment with my period 3 class. Okay, I'm not going to tell them that's an elevator question and see how it goes. I would put money on it going way differently. Okay, because if I don't say it's an elevator, people forget about gravity. Okay, well, let's have you guys do number 7 and let's go 5 and 7. Okay, so 5 and 7 both require you to do a little bit of kinematics as well. Okay, like they give you velocities and distances and times. So you might need to calculate acceleration before you can get to the Newton's second law step. Okay? And that happens a lot in this unit where we have to go back and look at the acceleration formulas from the last unit. Okay, so 5 and 7. Okay, so if we're looking at number 5, okay, all there is to it is that we have to do an acceleration calculation first. Okay? They tell us VI is 0 meters per second, VF is 25 meters per second. These are all south okay, and the time is 10.0 seconds, so I just have to go a equals 25 minus 0 over 10, so I get that the acceleration is 2.5 meters per second squared south, okay, and then I have the mass here, right, and all I have to do is go F net equals m times a, right, 2.5 times the 925, okay, and I get 2,310, or 2.31 times 10 to the 3 newtons south. Okay, everybody all right with that? So sometimes you get that, or sometimes you calculate the acceleration of a situation and they're like, how far will the object travel in the next 10 seconds? Okay, and you'd have to go back and do an acceleration formula, okay, something like that. It's like a part B to a question. All right, good job today, guys. We'll call it a day there.